Hello everyone. Today I'll present my poster. My name is Dr. Arundhuti Banerjee and I'm a postdoctoral fellow in TUDEV. So it's a short presentation. Now, data assimilation has been used extensively to provide forecasts and state estimates, combining model predictions with observational data to produce an optimal estimate of your state. So it relies on a model. It can be a numerical model or a mathematical model, as well as observation. Now, this model often contains certain static parameter values. And an incorrect representation of this static parameter value can give you erroneous state estimates and forecasts. This is exactly what we've investigated through our work, how the application of data assimilation can be used in numerical models, considering parameter uncertainty. So if you see, the model that we are working on is a mathematical model that simulates the behavior of two tectonic plates that are moving against each other, and it undergoes a stick-slip mechanism giving rise to earthquake-like events. So as you can see over here, it shows the basic data assimilation framework. C shows the data assimilation process using a result from the work by Van Dinther et al. 2019, where they used data assimilation for a numerical model used for representing earthquake cycles, and concluded that observations and prior physical knowledge from the model can be effectively integrated through data assimilation to provide better and improved state estimates and forecasts. As you can see in D, that becomes your analysis. In their work, their states were the stresses and the velocities at the fault. The approach that we're going to use in our work is a Bayesian approach, a probabilistic approach. Now, as per Bayes' rule, if you want to determine your updated state value, you have to multiply your prior PDF with your likelihood of the observations. The prior PDF is nothing but it contains all the information of the state before the observations were available. Likelihood of the observation is nothing but the probability of your observations occurring given X is your true state. So basically, if you have a prior PDF and you have a likelihood of observation, you can multiply them both to get your updated state or the posterior PDF. In our work, we're using a particle filter. The basic idea of particle filter is again to represent or to approximate this entire PDF in the form of particles or samples. So as you can see over here, it has been the prior PDF P of X has been approximated using Monte Carlo samples through a Dirac delta function. Now, there are three major steps involved in the particle filter. Firstly, the initialization step, where you start with an initial guess of your state. Then you propagate these states further with time, and sequentially you correct or update your states to the resampling process. Now, the process that we're going to use for considering parameter uncertainty in our work is the classic state parameter augmentation approach, where you incorporate the parameter inside the state vector itself. The model that I discussed previously is a mathematical model for forecasting seismic cycles. So basically, you solve these equations of motion in the form of three ODEs, where theta is a frictional state variable, U is the slip of one plate with respect to another, and V is the slip rate or the velocity of one plate moving against the other plate. So basically, you have three state variables, and they're all in non-dimensional form. If you want to find out how dimensions are calculated, you refer to the paper. And there are three important static parameters involved in this model. They are the epsilon, gamma, and psi. But we are basically considering the parameter uncertainty for epsilon. Now, how epsilon affects the state estimates, you can see the evolution of states with time by varying epsilon values. So you can see it can actually increase the amplitude or decrease the amplitude, or it can also increase or decrease the frequency of your state with time. That's how it kind of interferes with your state evolution. So this slide shows the physical significance of epsilon. Now, the simulation that we conducted in our study is, firstly, we generated the observations synthetically through a twin experiment, where we used the model itself to generate the observations. So we used a correct value of parameter epsilon to generate the observations. But in the model for state evolution, we used an incorrect value of epsilon as 0.5. So you can see the evolution of the states with time. And since the parameter in the model is incorrect, you can see that at certain time epochs, the state shear stress trajectory kind of falls out of the true trajectory with time. So you can see it is not very aligned with the true trajectory. Now, if you see the posterior distribution function for the shear stress state, you can see that each over here, that at certain time epochs, 22 and 24, you can see the observations are away from the particles. So the particles are not able to capture these observations because of an incorrect value of epsilon in the model. Now, when you consider parameter uncertainty, as you can see over here, you can see that the shear stress trajectory kind of follows very closely to the true trajectory with time. Over here, each particle or ensemble member, you can see, represents different value of parameters. That's how it's considering parameter uncertainty. And you can see it gives you an improved state estimates and forecasts with time. So basically the main conclusion from our work is that without parameter update in seismic cycle models with poorly known parameters, data assimilation will remain limited in its ability to capture the true time evolution of the seismic cycles. For future work, we tend to investigate this work further for a high dimensional system and also considering aperiodicity. And for the parameter estimation, we might choose a smoother approach or a different kind of approach apart from the state parameter augmentation approach. Thank you so much for listening to my presentation.